Here we are asked to use differentials to answer the question of how accurate we need to measure the angle to get the height of the building within the tolerance that's listed there, the 4%. So I like to start by drawing a quick building. Here it is. Here's your guy. He stands back here. The problem says he's 30 feet from the building here. And he's measuring the height of the building by looking up to the top of it. And we'll be measuring this angle, theta. So let's pretend the guy's face is like right on the ground so we don't have to consider how tall he is. And so we'll just pretend like it really looks like this. The theta here. In theory, they're the same theta. Okay, anyway, how accurately must this angle theta be measured for the percent error in the height to be less than 4%? So we can write that as an equation. What we really want to have happen is that the error in the height, the change in height, to be less than 4% of the actual height. And we don't care what sign that error in the height is, so we can call that absolute value. But we want to find the error to be less than 4% of the actual value. So then we have to look at the picture and decide, like, how do we even get to height at all? How will we find an equation for height? This guy is looking, we have a theta. We want to know the height of the building, h, and we have this side here, the 30 feet, which is adjacent to theta, and h is opposite of theta. So we have a theta, an opposite, and adjacent. Let's use the tangent. The tangent of theta is the opposite over the adjacent. In terms of this variable, the opposite side was h, so the tangent of theta is h, the height of the building, divided by the 30 feet, how far he was from the building. So we can solve that for h. H is 30 times the tangent of theta. Now we have an equation for height, h. We can then take the derivative to talk about the change in height, or the tolerance. The change in height is the change in the right-hand side. The derivative of 30 is still 30, but the derivative of the tangent is secant squared theta. Inside stays the same times the derivative of theta, or the change in theta. Well, now that we know these pieces, we have a dh formula and an h formula, we can rewrite our tolerance statement to say that the absolute value, the change in dh, is this 30 secant squared theta times d theta. That must be less than 4%, 0.04 of the height statement, and where we decided that height was 30 tangents of theta. So now we just need to solve for d theta. That's the thing we would like to know, how accurately we need to measure theta. So 30 is always positive, secant squared is always positive. Those guys can bust right out of the absolute value. Secant squared theta times the absolute value of d theta is less than 0.04 times 30 tangent theta. And on the left they are multiplied, so to get them over to the right hand side we'll divide. D theta, the change in theta, needs to be less than 0.04 times 30 tangents of theta divided by 30 secant squareds of theta. Of course, the theta 30s can at least cancel. And then we might want to investigate this tangent secant business. Let's do that on the next line. Absolute value of the difference in theta, or the estimated change in theta, is less than 0.04 times tangent theta sine theta over cosine theta. And secant squared in your mind is 1 over cosine squared theta, but to get him up to the numerator we're going to have to flip him over. So that would be times cosine squared theta over 1. And get rid of 1 cosine theta. D theta needs to be less than 0.04 times sine theta times cosine theta. So that's how we know the accuracy of theta. Now we have an initial value for theta. It says that theta started to be 75. So the first time he took this measurement, he found it to be about 75 degrees. So let's see what happens when we evaluate this derivative or this statement at theta equals 75 degrees. So plug 75 degrees in there, and you will find that d theta needs to be less than 0.01 radians once you move it back into radians from degrees, because calculus happens in radians. So we now know how accurately we need to measure theta.